Okay, so I think we can begin. So we're happy to have Jasper here from Van de Kreeke, is that it?
Yes.
From Amsterdam, soon to be from Berkeley, who will be speaking about Namikawa-Weyl groups of quiver varieties. If somebody wants to come in. Take it away, Jasper.
Welcome everybody also from my side. And so it's my pleasure to be here today. I would also like to thank Travis Shadler for making it possible to come. So that's a really kind invitation for this week. I've already realized this is a bit of like there's a lot of expertise already here at Imperial College. So Amihai's group and Travis Shadler are really working a lot on quiver varieties from all kinds of views. And my plan is to share something with you, but keep this relatively open. So I have some ideas, and you have some ideas, and I try to make a relatively informal, open talk about this. So here's a bit of my vision. Let's see. It's the best 10. We have geometry. We have category theory. We have algebra. Some stuff you study in geometry is stuff like manifolds or varieties. For example, here you have a point in such an algebra and such a geometric object we would like to see what it look like locally classified as. Category theory. You, for example, have modules, algebra, or sheaves, coherent sheaves, maybe of some variety, something like that. You'd also like to try to do that locally, huh? But what does it mean to inspect a category locally? I personally don't know. Maybe you have a clue. So, for example, you might have something like local objects which correspond to something like here in geometry locally, like local coordinates, something like that. Maybe you can do some describe the whole thing by the derived category of some small objects or something like that. And algebra. Yeah. What does one do in algebra? One studies, for example, algebras, rings.
I think you need a better pen, by the way.
Which one should I take?
If none of them are good, I can go get some more. There's also some over here.
In algebra, maybe we study algebras, like, for example, quiver algebras and their quotients. So, for example, this thing called pre-projective algebra. Who of you has seen this algebra before? 1, 2, 3, 4. Not all of you.
Well, it's not true because I mentioned it in my talk, but people don't remember. Maybe some people weren't here for my talk.
Okay.
They've seen all of them. Have seen.
Okay.
Could you repeat that, Amihai? This? Okay.
So everybody has seen it, whether they realize it or not.
Enjoy.
But you'll find here in London, at least in Imperial, that when you ask people a question, some of them will just not answer it. So it doesn't mean that the answer is no.
But I will always encourage people to speak up. So there's also yeah. What?
Then I will. This is my first time now with this people, and so just on a notational point, the Q bar in this notation.
Yeah, the Q bar means double quiver. To start up with we can do this also in a moment. Sure, I explain some more. If this is your quiver, you've seen quivers before, maybe. And this is your, maybe we call these arrow A, arrow B. You add for every such arrow, you add another arrow, which we call A star, B star, just in the opposite direction. And it's Q bar. Yeah, fair enough. Okay, so here's some bunch of objects, and maybe classical geometry, maybe Grothendieck already, of course, like thought about this stuff, but that was like 60, 70 years ago. Nowadays, you can do symplectic geometry with this. This one, symplectic geometry. Sorry, guys.
I can go get another more. There's more also in the window. There's several places we have markers, but I can go get more if they don't work. This is a really annoying thing about
I see.
materials, and unless you remember to
We'll go through all.
which I didn't.
Yeah, of course.
I mean, I will, yeah, you can try something. I will go get my markers. Okay. Right there.
Good. So nowadays we can do symplectic geometry with that. And we can do so symplectic geometry is a classical thing. Symplectic category theory and symplectic algebra is maybe a bit newer. And what's the closest thing? How can you, who knows, how would you define, like, what is the symplectic algebra? Or something which resembles symplectic? What a suggestion. Poisson bracket, okay.
Calabio2 category.
What?
No, it will not be like a Calabio2 category.
Yeah, good. Good. So Calabi-Yau properties, for example. Calabi-Yau. Yeah. This algebra is a Calabi-Yau algebra. If we take the representations of that, the modules, we get a Calabi-Yau category. Like, for example, cyclic A infinity category, for example. So this is the way, that's kind of my vision, that we need to be able to go from this to this to this, switch between, and go from local to global. And in that's my long-term vision also for myself to learn in the coming years. And in that regime falls the topic of today, Namikawa-Weyl groups for quiver varieties. So today, which you think good? Awesome. Let's try out some. So today, no hardcore algebraic geometry. I basically decided to do no deformation theory, even though that's where Namikawa-Weyl groups come from. Also, I think we will almost do no symplectic geometry, even, but we'll be very concrete and we'll do quivers. We'll see some resolutions of quiver varieties and Weyl groups. So something like see where Lie theory appears nowadays. Yeah. Awesome. So what's this talk all about? So the goal is to have some understanding of quiver varieties. And their resolutions. Right. Progress with the markers, if you know. Who of you, let's see. Who of you, okay. So let's talk about singular algebraic varieties. We'll be talking about singularities today. Who of you has seen singularities in varieties before? Raise your hand. Raise your hand. Oh, okay, good. Yeah, two. Travis, yeah, a lot of you. So you were able to answer this question. So recall that. Recall that an affine variety is a set of points cut out from C to the N, for example, cut out by some polynomial equations. So for example, let's draw this one. Singular or smooth?
Y equals x squared.
Yeah? Smooth? Okay, smooth.
Which ones were the ones I was supposed to try? No, maybe.
Those ones I brought them. They have the word.
6 more times I used them.
So these are all bad, these ones.
X, Y is 0, your coordinate axis. Singular smooth? Singular. Okay, what's here? Yeah, here's a singularity, isolated singularity. So that's singularities, how you do them in one dimension. So that's one complex dimension here, maybe. But we want to do singularities in more dimensions, higher dimensions. So who knows some singularities in 2 dimensions?
We all do, actually.
Yeah? You want to name some, Travis? Some which the audience should know?
Duval singularities.
Good. Okay. So before we have them, let me see. So if I have a look at 3 variables.
This is the tricky thing about asking questions. Like I said, sometimes people don't answer it, but they
Yeah.
can answer it either because it's too difficult or too easy.
Okay.
So if it's not exactly the right level of question, you have trouble.
But,
Yeah.
okay. Singular smooth. Singular smooth.
Singular.
Okay.
Pierre, it's unfair you're teaching this.
Yes,
to
exactly. So I do that actually.
Singular smooth.
Is that minus a z at the end?
-1.
A minus one, yes.
Yeah, in Britain, you're right. Like,
No, you can do it that way. I just I didn't quite.
in
Like-
Germany, they like the.
Yeah, it becomes
the-
it becomes a tenth at some point.
Yeah,
Yes.
singular smooth.
Smooth.
And here's another one. So this one you know. That's a Duval singularity.
So it's singular.
Onion.
Like Duval was at Imperial at some point in the past,
Okay.
before the logo changed to the new font.
And who can draw the picture?
I would just draw a cone.
Yeah. And why? So this is not immediately a cone, but I think if you do this parameter transformation.
I guess for us, most of the singularities are at least locally conical, if not cones. Just as long as you have this dilation action, and you have quasi-homogeneous, the cone.
Cool. Algebraic geometry, which I never knew. So, yeah. Some mathematicians have a classification of this stuff, right? So, classification.
Probably physicists do too. They'll tell us.
Who found, okay, good. Who found the simple, so the simple, what is it, simple 2-dimensional or hypersurface? What's part of the classification? Simple 2-dimensional singularities. After isomorphism locally
Wasn't it
isolated.
Klein or?
What?
No. Was Duval then? Was it?
Yeah, so the Klein singularities. So you've all seen the formulas? Yes, no? Good. So beyond this, I can never remember them by heart. So Who can remember them by heart?
I remember the letters. Everybody can remember the letters by heart. Yeah,
Yeah.
Amihai knows the equations,
Okay, E6, E7, E8. Okay,
but you don't have to write the equations. It's okay. We'll take your word for it.
good. Now, quiver varieties. Who of you have seen quiver varieties before?
Everybody has.
Everybody has.
They're also called the Higgs
I-
branch of unitary gauge theory.
Awesome. So I put, this is my quiver.
Unitary quiver, perhaps. Yeah. Higgs branch of unitary quiver, they say.
This is my quiver. So a quiver is an oriented finite graph, right? I take a quiver and I take a dimension vector. So for example, I take this quiver, I take dimension vector. So dimension vector means I attach natural number to every vertex. And I will look at the representation. So the 10-dimensional representations of that. So that's just attaching 10-dimensional 10 by 10 matrix.
Mhm.
The representations of this up to isomorphism are what? Okay, good. The representations up to isomorphism. Jordan normal forms.
Yeah.
Which is also the reason I think why they call this the Jordan Jordan quiver.
I believe so, yes.
Yeah, good. In general, a morphism between representations means just to go from, like, in this case, C to the 10 to C to the whatever below, such that going arrow here and then down is the same as going down the morphism and then going the arrow.
Yeah.
Yeah, double quivers. If you have seen quiver varieties, you have also seen double quivers, but I'll write this down nevertheless. So Q is a quiver. Double quiver. Just means for every arrow. Yeah, the start arrow, reverse direction. So this way, we get some interesting spaces.
Right, right. This the moment map condition. The fact that it gives you a representation of the projective algebra. You're gonna input.
So, yeah.
Yeah.
Okay.
Mathematicians can do this too, by the way. Yeah.
So when
So Pierre was England.
physicists talk about a quiver, they mean a quiver with relations. Mathematicians talk about a quiver, they mean a finite direct graph. Someone agree?
Not so different, actually.
Good.
Yeah. I mean,
So superpotential. So I know the construction of quiver varieties by using like moment maps. So
it's okay. You don't need to use the superpotential. You can just continue with what you had planned. Unless we need the superpotential. But yes, we had a discussion about it last time when you weren't here.
Yeah.
But let's save time because I want to try to get this done by noon so we can
Good.
lunch.
Yeah. The representation. So the row of A is the matrix attached to arrow A. Anyone can phrase this better than me? Okay, good. So representations, let's write it this way. So representations of the pre-projected algebra of dimension A is the set of row representations of the double quiver, which satisfy this. What else? Also, roughly everything that goes out of a vertex and then you go in again via all possible way. Yeah, so so out and in via the same, but summed over all arrows minus the other way around. That should be zero. So like the total flow in and out of vertex.
So yeah, maybe the important thing just to say here, or maybe just to write, is
Yeah.
that this row is assigning you a linear transformation or a matrix to every arrow.
Yeah.
Okay, if that wasn't clear.
Yeah. Good.
That's important.
Yeah, I was since everybody apparently knew quiver varieties.
Yes, but
I skipped a
what
few steps.
yes, this is true.
With
Everybody
the
knows
short-
curve varieties, but not everybody thinks about it in the same way.
Ah, good. Good. So, I've already mentioned this thing. Project of algebra. Yeah, too. Good.
And that's something that maybe not everybody knows, but that's okay. Maybe it's
Yeah.
not important.
That's good. Yeah. So algebra, kind of the
So in
close
case,
name.
how many of you know what a Calabi-Yau algebra is? Anybody? Yeah, some of you know. So it's something you could, one way to think about it is it's something so that if you look at its modules over it, then you get a symplectic singularity. That'll be one way to think about it.
In physics, they just call it the equation because of the symmetry.
Ah, okay. All right.
So here's a definition of quiver variety associated with a quiver and a dimension vector. So you take the representations of the double quiver which satisfy the pre-projected equation, and you divide out in the GIT way by GL alpha, which is the group whose orbits are the isomorphism classes. So the group, you all know how the group acts, don't you? On representations, yeah. So in the front of an arrow, you act by the group element there, and on the tail of the arrow, you act by the inverse.
So in fact, this pre-projective algebra is basically the only example in some sense of a Calabi-Yau too. So if you take any complete one, it is isomorphic to the completion of this. And you can have some global Calabi-Yau twos which are not isomorphic to this, but if you're able to complete it somewhere, then you'll get something isomorphic to this.
Thanks, Travis.
For Calabi-Yau, you have quiver with super
Yeah,
potential.
exactly. So this thing that Amihai was saying, if it was relevant for Calabi-Yau 3 algebra, so this you could soup this up to a Calabi-Yau 3. In Calabi-Yau 3, instead of just an algebra, you have an algebra. You have an algebra with this potential. So it's usually an algebra defined by a potential. But here, I guess the potential is the relation, if you like, in the denominator. But for Calabi-Yau 3, instead of just modding by relation, you mod by all derivatives of an element called a superpotential. All first derivatives. Yeah. But yeah, you can soup this Calabi-Yau 2 up to a Calabi-Yau 3 as well.
Here's an example. Who knows this quiver setting? This quiver.
They're writing the type A here.
That's the H1 extended H1 quiver.
Extended or affine type A.
Okay.
So we're all fine with it. The quiver examples, we're going to be perfectly fine with that.
So you know what comes out here and why? Yeah, good. Once we divide that out. So first, pre-projective relations are just tuples like this. Such that one. And so who can tell me the invariant functions? And when you do a GIT quotient, GIT means you look at the invariant functions under the group action. Who can name one?
Second.
Good.
You are 1 and 2.
Yeah. Also the opposite direction. And by means of a Reynolds operator, you can show but they generate already everything together with which one?
Okay, just 2 cycles.
Yeah. So this is it's the same as saying this. Okay, and the relation among them is?
That's when you take like, I think it's z power 5 is equal to xy.
Yeah.
So just.
Fine. Yeah, so this gives you linear neighbors. Good. So conclusion. Finding singularities can all be realized as quiver varieties. That's not only true for the A-type quiver, well, for the A-type quivers, you can do this for all the others as well. So you have some specific quiver settings, Q alpha for all the Kleinian types. And yeah, of course, one wants to play with that. So here's maybe something about their structure. So yeah, quiver varieties have symplectic structure. Where does it come from? Good, yeah. So because we've done this dual construction that we've made the double quiver, we have essentially we have that on rad Q alpha. Can write this as T star of rad Q alpha. There's canonical symplectic form here. And where does it descend? So where does it? So let's see here for. Why does it descend? So omega descends to a quiver variety. Why? Who showed that? Yeah, true. So if it's singular, then it still descends to the smooth locus, right?
Yeah.
Yeah. And where is that? That's 50 years old. This idea that you can descend some symplectic structures to quotients by groups.
Studying Manford? No, it's JT code.
It's
It's
not
an
yet
hyperscalar
one.
quotient in this case.
What?
It's hyperscalar quotient in this case.
Yeah. What? Good. Okay, I'll write that down. As I know it, but as I know it, it's a Master-Weinstein quotient. You say Weinstein or something like that in your German, yeah?
Weinstein, yeah, maybe, probably.
Yeah. Yeah, so the slogan here is that the zero set of a moment map might know that group. If there's Hamiltonian action by that, if the action by the G is Hamiltonian, then that thing, your symplectic form descends there. Questions? So symplectic singularities are great. Also for physicists, because you want to do phase spaces, and so you'll always be delighted to find some examples of these phase spaces, even if they're singular or something. So phase spaces are great, and they have a symplectic structure. You know that, so Hamiltonian equations you can formulate nicely. It's a Hamiltonian vector field. So XH. The Hamiltonian vector field, and through omega corresponds to the Cartan derivative of Hamiltonian. So omega symplectic form is what gives you the Hamiltonian vector field and symplectic manifold from the Hamiltonian. And so we have symplectic manifolds. They're locally, you have the Darboux theorem. The symplectic form looks locally like this. You have maybe smooth varieties. If omega is holomorphic there, Travis, is it correct that there is a holomorphic Darboux theorem. Mozart's trick and such there.
I mean, formally locally or analytically locally, yeah, it's to be true. But
Maybe some
Not good.
Italian.
but our algebraic variety is atal local, right? For analytic, you could think of it analytically locally, formally locally, yes, then you would have this statement. For manifolds, it's also it's also some local statement.
Thanks, Travis.
The Darboux theorem, it's always local. So for a manifold, it's around a compact subset or something of your manifold, and then which you could take to just be a point. And for varieties, it's an analytic or atal local statement. But in general, I think the global situation could be complicated, right? Like even classifying holomorphic symplectic structures on Cn, or for all I know, even smooth symplectic structures on R2n. I don't know if it's just the standard one. I have no idea about that.
So one wants to do singular algebraic varieties with symplectic form. So here's basically the answer by Weyl. So symplectic singularity or symplectic singular algebraic variety is algebraic variety over C. Let's take over C with holomorphic symplectic form on the regular locus, the smooth locus of S. You just say on the smooth locus, and that's easiest, but it typically suffices with some technical conditions. I'll not get here. So finding or devout singularities for varieties. There again, class symplectic. Good. So we've landed in the world of symplectic singularities. Now I wanted to show you magnifying classes for symplectic singularities. In other words, resolutions.
By the way,
Yeah.
as you know, Kleinian or Duval singularities, as we said, they're two-dimensional. But in fact, these inclusions are all equalities for two-dimensional cases.
Good.
At least
So-
at least locally, right? I guess you could have some global surfaces with Duval singularities which aren't given by a quiver variety, but yeah.
Oh, they also actually by volume.
Find symplectic form from that, right? So
Yeah.
yeah, nothing against that. Okay. So
We slightly extended it because we also did with normal
I see.
heat functions. Even though for the geometry varieties, I think they're originally.
Yeah, I think that's true, yeah. But what does happen even for Nakajima quiver varieties is you can have a leaf closure which is not normal. It's easy to happen, you know examples obviously of this. So you have to either generalize to non-normal symplectic singularities, or you can always be taking normalization, and the normalization will be a symplectic singularity.
Okay. Not sure whether it's too low in the corner, but here's our A1 singularity. Here's the resolution. And who can tell me what the special fiber is here? The special locus. Special fiber. So the fiber above the singularity. Good. Yeah, so that's the one which has come in here. And you can tell me what that is in coordinates. So 0, 0, 0, and which UVW? What's above 0? So if we have all x, y, and z 0, what freedom of u, v, and w do we have? The formula is on the board already.
Yeah.
Usually minus w squared is 0.
Yeah, it's
And-
just saying that if you have a cone, right? And you blow up the cone point with a cone, you get the projectivization of the cone sitting over the cone point. Right.
This is exactly a P1. I can in fact give you the exact identification.
Right, which additionally in this case, it's a quadric in P2, which is smooth, so it's isomorphic to P1.
Awesome. So that's a general theorem. So theorem, the exceptional, how do you call this thing? Special locus, exceptional fiber. And I always forget special fiber.
Well, yeah,
Special fiber.
different words for it.
Yeah. So for a Kleinian singularity, the special fiber is a bunch of P1s. So, and many intersecting the shape of the Eaton diagram. For the Kleinians. For the Kleinians. For Kleinian singularities, and there are symplectic resolutions, Kleinian singularities. So here's step 1P1, but for the A4 case, that will look like this. Or algebra geometrically look like this. Complex lines. How do you say? Complex projective lines intersecting. There's a surprise. I think Palladian and Namikawa. The same kind of story holds for other symplectic singularities, high dimensional symplectic singularities as well. So you have something high dimensional like this, and here's maybe your smooth locus. And what they say is that every symplectic singularity decomposes into strata. And the smooth locus is the top dimension 1, 0 codimension. Here you have codimension 2 strata, maybe codimension 2. I've drawn here. These edges would be codimension 4, codimension 6. You only have the even codimensions. And there might be a lot of these strata. That's local structure, and normally, to me was because a priori, when it has such a high dimension space, it's not clear what it looks like locally. Well, the stratification maybe is not such a big surprise, but that that locally around a thing in the codimension 2 stratum, the whole singularity, so the whole the variety itself locally looks like smooth times a Kleinian singularity. That was a surprise to me.
To
So
you,
locally,
yes, but
yeah.
but this is so there's two different statements here, right? There's a statement that, so of course you can define these symplectic leaves in general, and they don't have to be algebraic, but you can define locally analytically a symplectic leaf, and then the statement is that locally analytically you have finitely many leaves in a neighborhood of every point, so that this stratification by symplectic leaves is actually finite and therefore in fact algebraic. So you get a finite union of algebraic symplectic leaves. So the fact that you have finitely many was proved by Koledin for a symplectic singularity. So there's this statement. And then there's another statement that says that if you have a symplectic leaf, then at a point of the symplectic leaf locally, you get a product of a symplectic disk in the leaf direction and a slice. And this statement is in the smooth setting. Smooth analytic setting is called the Darboux-Weinstein theorem, and then Koledin proved a formal version of this for Poisson varieties.
I see. So there's a much more general way in which you can do stratification. So for Poisson variety, you can also Poisson manifold even you can also do a stratification by how
Symplectic leaves, yeah.
by how
It's
non-degenerate.
just that these don't have to. You don't have to have only finitely many of them. It doesn't have to be a finite. So I mean, sometimes when you say stratification, you mean a locally finite collection of strata. So if you mean that, then it's not a stratification in general. But
Great.
you always have symplectic leaves. You can always integrate the Hamiltonian flow to get symplectic leaves, at least locally analytically. And then there's this theorem that says that along with symplectic leaf, you have this product decomposition. And in this case, we have finitely many, so we really get in fact, globally finite stratification by symplectic leaves. And then this Darboux-Weinstein theorem says that, which Koledin proved. In the algebraic case, formally locally, you get a product decomposition. That make sense?
So please come, you showed an example of such a thing, and you already made a point for
Breeskorn, I'm forgetting exactly.
he had an example of
Oh, I see, yeah.
So Dick on the first coin, he's showing the coin. You have to be a prime.
Yeah, so this result you're talking about is saying that if you have a nilpotent cone, then the codimension 2 symplectic leaf has a Kleinian singularity along its slice. But these statements here we're talking about are not just limited to the codimension 2 case. In the codimension 2 case, another thing you could say is that in order to be a symplectic singularity, you have to have a Duval singularity along codimension 2. But this Breeskorn thing, it's I think it's probably proved more explicitly than just saying that you have a Duval singularity. They're actually giving you a construction of a slice, I think.
To ask something?
Yeah, I don't get what was the picture drawing.
Good. Who can answer this? This picture? So that's a stratification.
What?
of X itself. So if X is
Unitarity.
then
Exists in stratification.
Here's an example of the given result.
yeah, this is just a drawing. I thought you're a physicist, you enjoy drawings better than some rigorous formulas. But also like I think this is this. Okay. You're in which direction do you work?
This is my PhD student.
I see. Okay, good. Yeah, awesome.
I have a question.
Yeah.
This this kind of formulation in terms of GIT and GIT functions and these stratifications in the main context of GIT.
So
Well, this is a general statement which could or could not be related to GIT.
Yeah.
Just a symplectic singularity.
good.
This
Good,
Grothendieck
exactly.
Brieskorn theorem could be viewed in the context of what I was saying, is saying that in codimension 2, when nilpotent is a symplectic singularity. But of course, since it's a symplectic resolution, it's globally a symplectic singularity.
Via orbital.
That was my question.
If
It is the same stratification.
If the certification is dual,
Yeah, I mean, because you have, in GIT, it's a way to find your stratification.
Yeah.
And it has this way, you can maximally say that in general, essentially, when you move to one of the strata, you're then saying, okay, I can use the one that I have, but I'm going to reduce, which is like saying, my symplectic on there is degenerate, and I'm going to cut out the direction of each degenerate. And then you have every point that's stable with respect to your reduced group. And so that's why I'm wondering, in the sense of is the same notion of stratification as the coordinate stratification, but into the estimate.
I don't actually know this. I don't think I know this stratification. I have to learn whether that's the thing.
I mean,
So for a general GIT quotient, you see this equips the quotient with a natural stratification. You mean not just by stabilizer type.
no, you do, yes, but you will.
Ah, well, that's the same.
It's exactly. Yeah. So I think this is both Crawley-Bovey and then Travis Shedler and Wim Bellamy. They investigate this case of
see.
quiver
Yeah.
varieties, for example.
So all that we added to the picture was to turn on the stability condition. So probably Bovey proved this result with zero stability. We said, okay, you can deduce it for general stability.
Very good question.
It's a stratification by Jordan-Holder type.
By decomposition type of the representation, which you can also therefore equivalently think about in terms of stabilizer of this group acting, the product of the general linear group. So every point of the quiver variety is a bijection between points of quiver variety and closed orbits with this mu being 0, and then this the moment map being 0, and then you look at the stabilizer of a point of a closed orbit, and that stabilizer is some parabolic, which is telling you what the decomposition is into simple representation. Or stable if you're doing theta non-zero, theta stable representation.
So this W, can you say W again?
Yeah. So given that locally symplectic singularity looks like smooth times Kleinian, the resolution looks like smooth times Kleinian resolved. So in particular, you will have n mini pn's here over every point. And so over every point in the stratum, you'll have n many p1s. N many p1s. And now you can look as you walk around in the stratum. So as you walk around here in the stratum, you can look which p1s are connected to each other, because locally, you see, locally the picture looks like these are p1s, so they're like cubes, you see. But globally, if you walk around in the stratum, it's possible that some of these tubes are connected to each other. Because the intersections remain, So this one can be connected to that one, but cannot be connected to this one, for example, you see. So it's the connectedness, yeah, if you go around, gives rise to Dinkin automorphism. Yeah, when you walk around in a loop. That's sigma. So sigma is a Dinkin automorphism, and as you know, so the automorphisms of the Dinkin diagram act on the Weyl group associated with the Kleinian type. So you take the invariance under this conjugation action, and that's WL, so that smaller Weyl group for every leaf. You take the product of these smaller Weyl groups over all the leaves, all the codimension 2 strata. Leaf is stratum, different word. And Namikawa said this W is the difference in a precise way between the universal Poisson deformation theory of X and its symplectic resolution. Yeah, so this W, defined this way, plays a very critical deformation theoretical role. So one wants to compute these groups omega W for.
And we had a speaker speaking about these. In fact, Alberto was speaking about this.
Who was the speaker?
Alberto, what's his last name? Just finishing his PhD with David Bensby.
I see.
He's sometimes around. He may not be around now.
Yeah. Good. So
Well, he's often in London. I don't remember when the next time is, but he's often in London just for a visit.
who knows what resolutions of this thing look like? You know?
I know.
Okay, good. That's an ability parameter. Yeah, and comes with math pi. And so you need to analyze. You need to analyze all the codimension 2 strata. And then you need to track what happens above these strata. Are some of these? You need to analyze what is the special locus. And
I'm confused why you need to compute all of this stuff and you need
Yeah, the codimension 2 strata, exactly.
Yeah, so
That is
all the
exactly.
only the we need to, yeah, so what are the steps to do this? Steps 1, find symplectic resolution. In this case, in quiver case, we've already done that. Find the codimension 2 strata. So quiver case. Yeah. Yep, as well. This is Travis and Bellamy.
In general, it's also possible that you don't have a symplectic resolution, but then you can do what they call a Q factorial terminalization, the most that you can resolve in a symplectic way, and that will be good enough. Q factorial terminal is the best you can do without failing to be symplectic. I explained this in this is a technical condition because there's a notion of factorial without the Q, which is equivalent to saying that your local rings of functions are unique factorization domains. This is a generalization of that condition, but that condition becomes equivalent to the condition that every hypersurface is locally cut out by one equation. And now we can replace that by saying that some multiple of every hypersurface has this property. That's called Q factorial. This is some technical condition, which
You can also see it from the
for the purpose of finding the Namikawa-Weyl groups, you don't need this Q factorial. You just need a terminal. Any terminal resolution will do. You don't need to be Q factorial. Q factorial will not touch the codimension 2 strata. It will only touch the higher codimension strata. So for example, if you take T star Pn for n bigger than 1, it resolves some locus of square zero matrices, which has an isolated singularity. This is already terminal, because there's no codem2 strata. That's equivalent. But it's not q factorial, so the resolution is just replacing it by something q factorial. It doesn't change the Namikawa-Weyl, because that only involves codimension 2 strata.
Okay, example, X is Klein in singularity. Who can tell me the value? Namikawa-Weyl, this W.
Yeah, exactly. It's the Weyl group. That's why it's called, that's why the Weyl is Namikawa-Weyl.
Good, because there's just one point in the leaf, right? So no monodromy, no ones connected. But here's another example which I want to go through with you, which I got from Amihai yesterday. What happens in this case? So this is the quiver, and I will directly draw the double quiver. It's a dimension vector. Yeah, good. So this is Q alpha.
Yeah.
I think MQ alpha is the quiver variety, and we'll do something. We'll make a resolution by adding in some stability parameter. We'll see what that means in practice.
Yeah.
The stability parameter which I choose here will have a negative entry here, positive here, and positive here. In my convention, that means that the modules, the representations which are stable, are generated by this vertex. So it should always flow from the minus to the pluses. There should be a lot of matrix entries here and less matrix entries here. Yeah, that's what stability means. So the points in here are the representations which flow from left to right.
I use the opposite convention.
Yes.
I don't think it will matter.
And so what are the codimension 2 strata here? Those are the strata of certain representation type.
Yes,
So
I hope it doesn't cause any political problem.
there's one codimension 2 stratum. And it consists of the ones which are, so if I label the vertices as vertex 1, vertex 2, vertex 3, look like S1, S2, plus a simple here, one simple, no, here I need plus S2 plus S3 different symbols of that one. So these three individuals are in M, Q, 3. And S1 is just the simple here, S2 is the simple here. So the representations which look like this are the stratum. And what's above them? So what's in M theta above them? So what is in M theta above them? Those are the representations which are theta polystable, or simplicity, let's say theta stable, and so flow from left to right, and semi-simplify to such direct sum, and satisfy the pre-projective condition. And I'll just give you a bunch of these representations explicitly, and then you can read off the Namikawa-Weyl group. So we need to find, so that's what's the type of that stratum? That's a D4 stratum. So we will need to identify, we will expecting to find this structure in the special locus. And I'll give you some representation from here and some representation from here, and I show you that one can in fact get from here to here. Right, so what's the representation? The one parameter family representations here. Aha. How did I obtain this? That's by some educated guesswork and by first doing this in the Kleinen case. I first had a look, what does the special look like special fiber look like in the Kleinen case, and then I tried to transfer this to this one locally. And what are the kappas here? So the kappas are just the entries of these arrows. So kappa and kappa star maybe here. So kappa, and which one's which kappa star? And the entries, so the datum of these three simples. So I took almost a direct sum, yeah, almost putting 0 here everywhere, and only the entries which are already in the simples, and I just added a bit. Yeah, I just added some entries such that this is pre-projected. Yes, such as the pre-projected condition. It is over 0. Yes. Not over 0 over the stratum, so over S1 plus S2 plus rho, something over there. Yes, and theta stable. You can check that, yes, because there flows a lot to the right, as you see. You will not find sub-representations anywhere on the right, anywhere on the which don't reach everything on the right. So that's a representation here, and I will.
So you explicitly constructed a particular theta stable representation in the fiber of this map, basically.
Yeah, exactly.
Very good.
So you have 3 parameters, K and 1 alpha.
So we have these, you're calling them kappa, right? So so what we've got is the point that we're taking the fiber over in the singularity. It's on some stratum where it decomposes as a sum of one-dimensionals. But now, since we have a loop, one-dimensional representation has some modulus. It has this kappa and kappa star, which can do whatever you want. So the parameters are the kappa i's for the 3 and the kappa star i's for the 3. So we have 6 parameters for the point that we're resolving. So fixing those parameters, and when we look at the fiber, looking at all the different ways that we can take extensions of these modules in a theta stable manner. And Jasper found one such way that he wrote on the board. Is that correct?
Yeah.
So 1 alpha and 6 kappa.
True.
The alpha is fixed. It's the dimension vector 1, 2, 3.
This alpha. I mean,
Oh, that's a different
that's
alpha.
Yeah, that's the one parameter family here.
Okay, sorry.
I could equally put a 1 here, but then you would not see that it's a one parameter family. So I put a 1 here.
It's a different alpha from the
Yeah.
dimension. So we have that parameter. So the point is that when we look at the fiber is going to be this union of P1. So the fiber will have a discrete parameter, which P1 we're in, and a continuous parameter, the point in the P1. So this alpha and the matrix is supposed to be the continuous parameter for one of the components.
Okay, here I've given you another family. And without proof, I will tell you it's this one. They're not the same.
So you've given us 2 different components, irreducible components of that fiber.
Good.
The general result is that the fiber for a client singularity, the zero fiber is a union of P1s which intersect according to the Dington diagram. Therefore, as we pointed out, if you have an arbitrary symplectic singularity, codimension 2 leaf, locally it looks like a Duval singularity cross a symplectic disk. The fiber still looks the same. One of these ADE things, a union of P1s intersecting according to this diagram. But the difference is if you have a leaf, which codimension 2 leaf, which is not zero dimensional, you can move around the leaf and you have some monodromy which swap some of these components. And whether you do it or not, it's telling you if your Namikawa-Weyl group is just the ADE type Weyl group or a folded type B, C, F, G. And that is what Jasper wants to detect.
We see it before.
So here is the two P1s are connected to each other, but here should be all the three P1s connected to each other.
Yeah, they are.
Yeah, in fact, they
This
are.
is connected to this one, and the other one I didn't draw for you, but if you were to continue the argument, you would also get this.
So you could have had an example with only two connected. So there's three possibilities. If your slice is a D4, there's three possibilities in this particular case for the group. There's the D4 group, there's the B3 group, or there's the G2 group.
Maybe 18.
For D4, I don't think you can fold it to A2.
No.
There's three different ways to
What
fold.
do you do with the change for the
In that case, I believe it's due GQ. Because in that picture, in the Fabric picture, you cannot see an additional P1 with only three P1. So the maximum we can get is S3. And this S4 somehow reduce the equal to S3.
So what do I do in order to show this, that these P1s are connected? I start with this representation, and I'll gradually change the kappa 1 star into kappa 2 and kappa 2 star, and kappa 2 and kappa 2 star into kappa 1 star. But I go the long way without ever hitting the diagonal, so never making any entries equal. And after I've done that, what will I arrive at? Maybe this is the chance to choose different color. I will arrive with kappa 2 standing here, right? And kappa 1 standing here. And kappa 2 prime standing here, and kappa 1 prime standing here. And so you see. And
Right, and you interchange also those coefficients at the top, right? Will also
this one, yeah. So this one will also
2 minus 1,
this
1
one will
minus
also
2.
go to some other. You see, and by doing that, I've always been above stratums, just walked around it, and the thing I end up with is precisely this one. It's precisely isomorphic. It's just another way of writing down these matrices. So just you conjugate by changing the roles. So I've ended up exactly here. So I've shown that these P1s are connected.
In other words, this path we went on is actually a loop. It's a closed path on the MQ alpha side, but moving along upstairs, we get a non-trivial automorphism.
Thanks. So here are the conclusions. We have analyzed the fiber of the stratum and found a general strategy how you can find Namikawa-Weyl groups. For me, this is another cornerstone in making something like going between representation theory and category theory, smooth versus singular. So yeah, you have desired to see some examples of Namikawa-Weyl groups. Yeah, I hope I have served you well. And yeah, I could not think of any better time for this thing. This is the final result is that all these three P1s are connected. So you know that the Weyl group is what's the name of that? G2. Okay, thanks.
Yeah, so the statement is that one can explicitly see the monodromy for the G2 group. So there's some different theoretical ways which all end up the same criterion that allow you to see that you get a G2 group. And Jasper is explicitly describing as monodromy.
Right. And I also have some strategy how to some strategies how to do this in more generality. But here's the pictures. So yeah, I'm really convinced, like with both Travis and Amihai working in this direction at the same time, I'm convinced there would be no better time to visit you guys and visit Imperial College than now. If you like this talk, make sure to invite me again.
All right, let's thank Jasper then. All right, so let's go get lunch. And